So our project is on carbon capture and sequestration. I'm Hayden Lopez.
I'm Mia Schultz.
And I'm Maggie Lynn. And so basically, carbon capture and sequestration, or CCS, is a three-step environmental technology process designed to combat climate change. First, we capture carbon dioxide emissions directly from industrial sources like power plants and factories before they enter the atmosphere. Second, we transport this captured CO2, typically through pipelines, to suitable storage locations. Finally, we inject and store the CO2 deep underground in geological formations like depleted oil and gas reservoirs, or saline aquifers. The goal is simple but crucial. Keep these greenhouse gas emissions permanently out of our atmosphere where they would otherwise contribute to global warming. This process essentially allows us to continue using fossil fuels while reducing their environmental impact. The concept of carbon capture and sequestration has evolved over several decades. The foundation research began in the 1970s when scientists first started exploring ways to manage industrial CO2 emissions. However, the real breakthrough came in 1996 with the launch of the Sleipner project in Norway, which became the world's first commercial scale CCS operation. This project showed that we actually can store huge amounts of CO2 underground, and it actually works. The 2000s marked a period of rapid development and expansion, with numerous projects and research initiatives launching worldwide. During this decade, governments and industries began recognizing CCS as a crucial technology for meeting climate goals, leading to increased funding and technological advancement that continues today.
So what are some current technologies and uses of CCS? One of the big ones is EOR, and EOR is enhanced oil recovery. And for almost 50 years, carbon dioxide has been used in this practice to extract additional oil from fields in the United States. And new technologies are also being developed to reuse captured CO2 in different ways, such as jet fuel and car seats. And for producing clean hydrogen, many experts see hydrogen as a pivotal clean fuel of the future. And reforming natural gases with carbon capture technology is the cheapest way of producing this clean hydrogen. And how it applies to Louisiana, the state we go to school in, the state a lot of us live in or are from. Louisiana faces great threats of climate change because of its coastal nature. And we've seen this through major storms such as Hurricane Laura and Ida recently. And sea level rise and land subsidence are also big factors that affect Louisiana. And petroleum and coal product mining are the biggest industry in Louisiana. And these industries combined, I guess, bring almost $21 billion annually to the state. And as is known by most of the general public, these practices generate a lot of carbon emissions. And the Louisiana Climate Action Plan was put into place by John Bell Edwards administration in 2022. And the goal of this plan is to reach a net zero in emissions by the year 2050. And another major goal is to decarbonize industry as a whole. And this plan has a group called the Climate Initiatives Task Force. And these people are basically leaders on the plan to identify particular issues with emissions and climate change and finding solutions as to how they can attack these problems.
Like any emerging technology, carbon capture and sequestration presents both significant advantage and notable challenges. On the positive side, CCS offers a proven method for dramatically reducing carbon emissions from existing industrial infrastructure. It can create thousands of jobs in engineering, construction, and operations while potentially improving soil fertility in certain applications. The technology has demonstrated efficiency rates in operational projects like Petra Nova. However, we must acknowledge the concerns. The process is extremely energy intensive, requiring substantial power to operate all of the capture and compression equipment. Also, costs remain high, making widespread implementation challenging.
So some of the pros, carbon sequestration is very efficient in storing carbon based on operational successes. And Maggie talked about Petronova. Petronova is a carbon capture plant in Texas, and it captured about 90% of the emissions from the WE power plant in Texas. This is a picture of Petronova. And additionally, soil carbon sequestration in particular provides increased soil fertility, productivity, quality, biodiversity, and reduced soil compaction.
The primary benefit of carbon capture is that it reduces carbon dioxide emissions. These emissions are responsible for a large portion of global warming and climate change. By capturing and storing carbon dioxide, we can reduce the amount of greenhouse gases in the atmosphere and limit the impacts of climate change. The deployment of carbon capture technologies can also lead to job creation in areas such as construction, engineering, and maintenance. This can benefit local communities to help strengthen local economies.
And there are some negatives to carbon sequestration. The carbon, it's not necessarily guaranteed to stay in the ground. Basically, the liquefied CO2 is kept at such a high temperature that it can seep through the ground and back to the surface and then eventually find its way back into the atmosphere. And this is a picture of Yucca Mountain in Nevada. It's a nuclear waste disposal site. And nuclear waste disposal and carbon sequestration are kind of the same way, in that we don't really know the future harm or the future ramifications of what's going to happen when you put these things into the ground or into landscapes. And site characterization is needed. Site characterization is studying an area in enough detail to where you know whether it's safe to inject things into the ground. And basically, we just don't have enough time for this. We only have until 2030 until major climate change, like irreversible climate change, sets in. And places studied in this detail have taken at least 14 plus years. And Yucca Mountain, it took 20 years for them to find out if the nuclear waste was going to stay in the ground there. And we just don't have that kind of time.
Some carbon capture technologies can also be an energy-intensive process. It requires a significant amount of energy to capture carbon dioxide and transport it to storage facilities. For that reason, there has to be a thorough planning and selection of the adequate technology to mitigate this con. Carbon capture still has a relatively high cost. The technology requires significant investments in research, development, and infrastructure, which can be extremely expensive. Research needs to be done to further develop to reduce research needs to be further developed to help reduce such costs. And here we can see the costs of these carbon captures based on the type of resource being used by energy production.
Now, do the costs outweigh the benefits? This might be the most critical question facing CCS and technology today. When we examine the costs, we're looking at billions of dollars in infrastructure investment, ongoing operational expenses, and significant energy requirements that reduce overall plant efficiency. The current price tag for CCS projects range from $50 to over $100 per ton of CO2 captured. However, the benefits extend far beyond simple economics. We're talking about potentially preventing catastrophic climate change, preserving existing energy infrastructure and associated jobs, and buying crucial time for renewable energy transitions. The Chevron project demonstrates that large-scale implementation is achievable. The real question isn't whether CCS is a lot of money, it's whether doing nothing about climate change will cost us even more. When we consider the economic damage from extreme weather, rising sea levels, and an ecosystem collapse, CCS investments begin to look like an essential insurance policy for our planet's future.
So, like Maggie just mentioned, the Chevron project here's the timeline for that. It's a real world example that we can see now. In 2009, off the coast of Western Australia, Chevron began injecting naturally occurring CO2 emissions into sandstone formalities where it still remains. This is Gorgon on Barrow Island, and it features one of the world's largest CSS systems. In 2020, Chevron began working with Savante and the National Energy Technology Lab, testing CSS tech at scale and discovering ways to make carbon capture cost less for the commercial market. The project received funding from the U.S. Department of Energy. In 2023, the Bayou Bend hub's onshore expansion became one of the largest carbon storage projects in the country. It now features a gross storage capacity of more than 1 billion metric tons. The Bayou Bend Storage Hub is located in the U.S. Gulf of America off the coast of Southeast Texas. So, according to the U.S. Environmental Protection Agency, carbon dioxide capture and sequestration plays an important role in reducing greenhouse gas emissions while enabling low carbon electricity generation from power plants, and has estimated in the U.S. inventory of gas emissions and sinks, more than 40% of CO2 emissions in the United States are from electric power generation. These large stationary sources of CO2, which include coal and natural gas fired power plants, as well as certain industry types such as ethanol and natural gas processing plants. CO2 capture is currently occurring over 120 facilities in the United States, mainly on industrial processes, and the CO2 is used for a wide range of uses. End uses of CO2 include enhanced oil recovery, food and beverage manufacturing, pulp and paper manufacturing, and metal fabrication, which is seen on the pie chart on the left. Potential sequestration sites must undergo appropriate site characterization to ensure that the site can safely and securely store CO2. After being transported to the sequestration site, the compressed CO2 is injected deep underground into solid but porous rock, such as sandstone, shale, dolomite, basalt, or deep coal seams. Suitable formations for CO2 sequestration are located under one or more layers of cap rock, which trap the CO2 and prevent upward migration. These sites are then rigorously monitored to ensure that the CO2 remains permanently underground. The safety and security of CO2 geologic sequestration is a priority for the EPA. And that can be seen by these regulations. These are just some examples of the strict standards that are enforced and characterized in protections and incentives. Some of the protections are governments will ensure that compliance with environmental and other protections as companies pursue CSS. These include protections for habitat and species, drinking water, historical and cultural sites, and other areas. The U.S. currently has no specific laws on CSS, but companies will have to navigate a complex network of state and federal protections in both of these, protections and understanding the often complex regulatory context so that they continue pursuing CSS. Some incentives are the government may establish mechanisms to encourage adoption of CSS strategies. At the federal level in the U.S., this is currently done through a tax credit detailed in Section 45Q of the Internal Revenue Code of 1986, as amended, that specifically targets CSS. In a recently enacted bill, these tax incentives were further extended to potentially allow projects that begin construction before 2026 to be eligible for tax credits. President Biden's climate plan would further enhance the 45Q tax credit and provide other financial incentives for CSS, which we don't know much about now. This is just based on an article I found in the past. So obviously things could change. And yeah.
So there are a lot of legal issues regarding CCS, and one of the major ones is it involves how the pumping affects the landscape near pumping sites. And this is the Stratos Air Capture Plant in Texas. And when you're drilling at sites such as these, activists say that it can increase the probability of earthquakes, blowouts, landslides, etc. And internationally, another one of the issues is it has to do with injecting carbon into international waters, into seabeds. And there's not really a set limit on where the cutoff line is and where certain countries can inject it. So there's been a lot of controversy regarding that. And there have been mixed public opinions about CCS, like there are with any major environmental issue. And one of the main examples is a group called Greenpeace International. And this group is in the United Kingdom, and they were strongly against the injecting of carbon dioxide into the North Sea around the country.
So, as we've seen throughout our presentation, carbon capture and sequestration isn't a perfect solution, but it could be a necessary one. The technology faces real challenges like high costs, energy requirements, and storage uncertainties, yet the climate crisis we are in requires us to try out every viable option. and CCS offers immediate potential to reduce emissions from existing infrastructure while we transition to renewable energy. The solution truly isn't black and white. We can't rely solely on CCS, but we also can't afford to ignore it. The key is using CCS together with other renewable energy sources, making buildings more efficient and changing how we use energy. Louisiana, with its industrial infrastructure and geological advantages, is equipped to lead in this technology. And when we realize that ignoring climate change will cost us way more than fixing it, the choice becomes clear. We need to tip the scale toward action and use every tool we have, which includes carbon capture and sequestration. And
And
then,
here we have our references at the end, and that is it. Thank you.
thank you.
Thank you.